Welcome, everyone. For today's prep, we're going back to our applications of definite integrals, and we're going to be looking at arc length, so how to calculate the length of a curve. And the reason why we went back, or why we kind of skipped over this one, is that the formula, it's going to be an integral formula, and it involves a square root. And so we needed a little bit more integration techniques under our belt before we could really do this topic justice. So now that we've gone through a lot of our more advanced integration techniques, we're coming back. All right, so first let's read through this. So let's suppose that we're looking at a curve y equals f of x, and we're only looking at a section of this curve. So x is between a and b, some endpoints a and b. Well, then the length of that section is going to be the definite integral from a to b of the square root of 1 plus the derivative of our function squared, and we're going to be integrating with respect to x. All right, and there are a couple other requirements here. The function that we're looking at, the curve that we're looking at, has to be differentiable, so we should be able to calculate f prime, and the derivative should also be continuous. And that's more of a technical requirement in order for this formula to work out. All right, so in this formula, we're treating y as a function of x. So x is our variable. And so when x is our variable, we end up integrating with respect to x. Now there is a slight variation of this formula, and that happens if we're kind of looking at a slightly different curve. So another option is if we have a curve that's in the form x equal to a function of y. This sometimes happens. Kind of like tilt our head. And we're looking at an interval from, say, c to d, where y is between c and d. Well, in this case, if we have this different formula, the length formula is going to be the integral from c to d of the square root of 1 plus the derivative of x with respect to y squared, and then we integrate with respect to y. So if we're given a function and the variable is y, well then we're going to end up integrating with respect to y. So sometimes we'll see this kind of slight variation. In any case, where does this formula come from? So let's actually look at a little bit the idea of how to actually prove this. We're not going to prove it precisely, but I think it's instructive to look at where this formula actually comes from. So let's look at the idea of the proof. All right, so let's suppose we have a curve. So this is our function here. And we're only looking at a section of this curve. So we're looking at just a section in between a couple different endpoints. So let's say we've got this endpoint here and this endpoint here. And what we want to do is we want to figure out how long this stretch of our curve is. We want to figure out that length. Well, the idea is that we're going to break this section of our curve up. We're going to slice it up into a whole bunch of little pieces. So we're going to find all these little, basically we're going to divide it up into a whole bunch of little line segments, or things that are going to look like little line segments. And let's zoom in on, say, just the end right here. So let's just zoom in on the little line segment at this kind of this one little section. All right, so what do we have? We've got our one endpoint, and we've got our one little slice that we've made, and then we've got the section of, actually let me make this a little bigger. So we've got our one endpoint, we've got our one little slice that we've made, and then we've got our section of the curve there. And the idea is we're going to end up approximating this little section here with a line segment. Okay. And so each of these little sections here, we're going to be approximating with line segments. All right, so then once we have all the length of these little line segments, they're going to be really tiny, but there's going to be a lot of them. So we're gonna add up all those little lengths. And that's what the integration does, is it's really adding up all the lengths of all these tiny little sections. So that's what the integration does. So let's figure out what is the length of this one little section. And we're going to form a right triangle. Okay, there's our right triangle. And the horizontal distance is going to be delta x. And the vertical height is going to be delta y. So change in y is vertical, change in x is horizontal. And we can figure out the length of the hypotenuse here with just a little bit of geometry. So the length for this section, length of that hypotenuse, is going to be the square root of the one side of our triangle squared plus the length of the other side of our triangle squared. And we can actually do a little bit of algebra here, and we can factor out a delta x squared from both of those terms. So if we do that, we're going to end up with 1 plus delta y over delta x squared times delta x squared. And you can check, if we distribute, the delta x squared would cancel off the delta x squared here, and when we multiply it with the 1, we're going to be back to where we started. And then we can simplify that ending term by bringing it outside of the square root. So we end up with 1 over, or the square root of 1 plus delta y over delta x squared times just delta x. That's what the square root of that delta x squared is. It just ends up simplifying to just delta x. So when we look at this, if we go back up to our formula, what we're doing is we're adding up. The integration is addition, and then we're adding up a whole bunch of these tiny little lengths. And that's what we're seeing with our square root term, and then our delta x at the end. All right, so not a rigorous proof, but just an idea for how the proof would work. So let's try an example, and let's start with actually example 2. So we'll actually go through and do the integration on this one. All right, so we have this curve y equal to x raised to the 3/2 power. X is between 1 and 3. So we want to find the length for this section. So let's try it out. The length, well, we're going from 1 to 3, and it's going to be the square root of 1 plus our derivative squared. And our formula here, the variable is x. So it's in the form y equals a function of x. So we're probably going to start this one off integrating with respect to x. All right, so let's figure out our derivative that we can fill in. And, you can probably just do this in your head. I'll do it off to the side here. So dy dx is, if we're differentiating our function here, we do a little bit of power rule, bring the 3/2 down, put it in front, and then subtract 1 in the exponent. All right, so that's our derivative. So we're going to fill that in. So we end up with the integral of 1 to 3. And we have our 1 plus that derivative squared. Now, when you do this, whoops, x raised to the 1/2. It's important that you remember the parentheses here. So I kind of intentionally left it off, or wrote these parentheses in, because when we have something like this, everything has to end up getting squared. So we've got some multiplication here between the 3/2 and the x to the 1/2. So this exponent can be distributed, essentially, to each of those terms. So when we simplify, we're going to end up with the integral from 1 to 3, square root of 1 plus 9 over 4 x. So we square the fraction to get 9 over 4, and then we square x to the 1/2 to just get x. So just be careful here. Remember parentheses. All right, so now we have this integral to do, and this is just a K-form power rule. So it's a power function, and it's just a constant k times x plus another constant. So this is just a K-form power rule. So this isn't too bad to actually get the antiderivative of. So when we go to do the antiderivative, we keep what's inside the square root or inside the parentheses. So keep it the same. We add 1 to the exponent, so that's going to bump us up to 3 over 2. Take that new exponent, flip it, put it in front, so we get a 2 over 3. And then our constant k here is that 9 over 4. So we end up flipping that as well and putting that at the end. Or you could put it at the front too. So this is a K-form power rule. We saw this this was one of our cases when we were doing integration by partial fractions. So we saw this a little bit there. So normally the fraction is 1 over k, but you can think of that as just the reciprocal. So 1 over k is the reciprocal in this case of the 9 over 4. All right, so once we have our antiderivative, and if you didn't want to think of it this way, you could also do this with a u substitution. So you'd let u equal what's under the denominator, or under the square root sign. You could do it that way as well. So we got our antiderivative. We're going to evaluate it from x equals 1 to x equals 3. And before we evaluate, not a bad idea, maybe clean this up a little bit, get those two fractions together. So we get 8 over 27, and then 1 plus 9 over 4x raised to the 3/2 power, and then we're plugging in from x equals 1 to x equals 3. So top number goes in first, and when we do that, we end up with, what do we get? We plug 3 in, and we get 1 plus 27 over 4. Raised to the 3/2 power. And then we subtract, and we plug in the 1. So we get 8 over 27, 1 plus 9 over 4, raised to the 3/2 power. Perfectly fine to just leave it like that. If you wanted to, you could add these terms together, add the terms together here, but that's fine. All right, so we get our length. So we'll practice more of this in class, but I just wanted to get a nice reminder here of our K-form power rule. So we've seen these a few times. So we'll see you in class. Bye-bye.